Nintendo Wii, the remote control, there's actually a camera system built right into here that tracks the 2 dots that are from the sensor bar and reports that information. But the real game changer in terms of computer vision being involved in games was the Microsoft Kinect. The Microsoft Kinect is a depth sensor. And what I mean by that is it can produce a scene like this. That is, it can produce an image like this from a scene. And this is a depth image, right? So darker is farther away, and brighter is closer, and gray here is sort of in between. These white stripes, these are where the thing is shadowed. Don't worry about that. So from a technology perspective, from a raw technology perspective, most people think that what was important about the Kinect was that it created a depth image. But you will know better. No. The important thing about a Kinect is that it can produce skeletal descriptions. Using a combination of machine learning techniques applied to computer vision, the folks at Microsoft, this came out of Microsoft Cambridge in the UK, were able to recover the skeleton geometry of people from the depth image. And by the way, they do it instantaneously. Every frame, they do it differently. They don't even track it. They just do it 1 frame at a time. It's that robust, right? And because they could get the skeleton information, you could build really cool user interfaces. So you could, do driving games and go like this to steer your car. Now, personally, I would get tired of that after a little while, but, if you're prepubescent, maybe this is a lot of fun. Much more interesting, of course, is playing with robots. And here you see, this is Simon in the, Andrea Tomas's lab here at Georgia Tech. And the reason Simon is waving to the student is that behind Simon over here, there's a Kinect that's looking at the student waving and is getting back the depth information, also the skeleton information, and is then interpreting the skeleton information in terms of what the human is doing, and that in turn allows the robot to make a decision about what the robot wants to do. So even though the Kinect was sort of promoted and invented as a way of impacting games, and early on there was some uncertainty at Microsoft whether they wanted to open up that system and let people use it, they quickly realized that this is something that everybody wants to use, and it has really revolutionized the way people think about depth imaging and computer vision applied to depth imagery. Finally, 2 more. Surveillance is a huge issue. This idea of being able to monitor environment for crowd safety, a variety of reasons. These are screenshots taken from Siemens sells a system for doing port monitoring, just to know whether, say, people are loitering or vehicles are approaching that aren't supposed to be. This is also computer vision. A more direct effect on a single individual of computer vision is work in medical imaging. Okay, so here you see an example. There's all sorts of 3D imaging, MRI, CAT scan, stuff like that. But here you see some work. This came out of Eric Grimson's lab a while ago at MIT, where on a screen, the computer vision system is registering the skull that's on the table with a model that has been created from the 3D imaging. So when the surgeon looks at this monitor, he sees the real person, and by the way, if there were a scalpel here, he'd see the hand with the scalpel, or a drill, or whatever you're using to make a hole in a person's head, and where the various structures are underneath that you wanted to see. And that's also computer vision. Look, this is just a quick taste of the state of the art. Hopefully it inspires you. One of the things I want you to realize is that almost everything that I showed you here is less than 10 years old, and in fact many of them are less than 5 years old. So the field is rapidly changing, and there's a tremendous amount of opportunity in computer vision right now. So this is exactly the right time for you to take this class so that you can invent some cool technology, make $3 gazillion, and send a very large donation to the people who made it possible. Quick, put on your entrepreneur cap. Think of a situation, maybe from your own day-to-day life, where computer vision could be applied that maybe isn't quite yet. Obviously, there's no particularly right or wrong answer. With computing having gotten so small and powerful, and cameras being so easy to produce and cheap, you can start doing computer vision all sorts of places. Look, you opened your eyes sometime, when you were really, really small, kind of fuzzy for a while, but after a while, you just saw. So you might wonder, why is this hard? Let me give you a couple of examples. So here we have what you think of as a simple scene, and this was generated by Ted Adelson up at MIT. All right, and you see on this screen, we've got this checkerboard here, and we've got this cylinder casting a shadow. All right, and there are light and dark squares. And you see these 2 squares, the A square and the B square. Which of those 2 squares do you think is actually darker? Okay, Well, if you're like me, you say, well, duh, it's the A square. Okay, that's A is dark and B is light. Maybe not so fast. All right, so here I have a gray bar, and this gray bar is the same intensity all the way down. And through the magic of PowerPoint, we're going to slide that gray bar over, and now we have a problem. There's no edge here, there's no edge there. And that's a constant gray bar, right? That means squares A and B are actually the same color on this screen. Really. In fact, if I put two of those bars there, you start to be able to see it. In fact, let me go back and forth there. You see that? When there's only one bar, your brain just wants you to believe that that's a checkerboard and that it's the cast shadow and that that's the light square. If you actually took a photometer and you measured, you would see that there are as many photons coming off of this region as off of that region. But the photometer doesn't have your brain. It doesn't understand. No, that's actually a light square in a cast shadow. All right? This is why computer vision is hard. So in that example, the thing to realize is those two squares that have the same measurement of intensity, right? So seeing is not the same thing as just measuring image properties. In fact, seeing is called, we refer to it as building a percept, build up a description in your head of what's actually going on there based upon what's in the measurements. That can be illustrated in a couple of ways. Here's one. So this is a very, very old stereoscope. This is a slide borrowed from Michael Black. And we'll talk about this in detail when we do stereo. And the stereoscope here is designed so that one image goes to one eye and the other image goes to the other eye. So here they are. And if you take a look at those two images, this is the left image and this is the right image. Left, right, left, right. It's the difference between those two images that lets your brain realize that the dad holding the kid is in front of the bed where the mom is. Okay? And it's that difference. You're building that description from the difference between those images. So I'm going to show you a video now from Dan Kirsten that shows you that perception is an active construction on the part of your head. So here, there's going to be this ball rolling back and forth, okay? And the ball is going to do the same thing, but the shadows are going to do something different. Ready? Watch. Whoa. Okay? So let's do that again. So you see the ball and the shadow goes with it, and you see the ball going to the back corner of the checkerboard. And now we move the shadow sideways, and you see the ball lifting up. The ball did the same thing in both cases, all right? But your brain, because of the shadow, says the ball did something different. So again, that's not a property of measurement. So here's another example. So what you're going to see is what looks like a green piece of paper or something on a checkerboard. You saw that green thing lift up, right? You saw it come right off the checkerboard, right? Let's do it again, all right? Here we go. It comes up off the checkerboard, right? Just look at the top left-hand corner of that green thing, and you will see that absolutely nothing moves. None of the green pixels move at all. The only thing that moves are those darkish pixels, which your brain says is a cast shadow. So that means your brain had to pretend there was some illuminant up in the sky over here making these shadows, and the only explanation is that the green thing came up off the checkerboard. So it's another example of your brain doing this construction. So the previous examples that I was showing you are in some sense the human system doing something wrong, right? The ball didn't actually change what it did. But actually what happened there is that there's ambiguity as to what the ball is doing, and your brain is creating the story. It is making the description. And the difference between straight image processing and computer vision is building that description. And we're going to show you some of the methods that you would use to help do that construction. So let me give you a little bit of a course overview. To do that, let me explain sort of how the course is thought of, at least by me, and Arpan thought this was really good, and Arpan's really smart, so if he thought this was really good, maybe it's good. You can think of computer vision as being a relationship between sort of three ways of thinking about what goes on. At the top of the triangle is the computational model. Often that's the math. And I'll use an example from stereo. So here we're showing you sort of the mathematics, geometry behind, if you have multiple views looking at a point out there, how you could reason about it and how what the math would be behind trying to find its actual depth, right? The idea, here's the center of one camera, center of another camera, here's some point possibly here, 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 and by matching, we're going to be able to figure out what the depth is. Once we have the math, we can develop an algorithm. So here's an example of doing stereo by what's called just correlating two patches along an epipolar line. Don't worry, you're going to learn what these things are. And computing, say, the sum of square differences, just how well they match, and you would measure that, and the point at the minimum, that's what this bottom point here is, that would be the right match, and by knowing that match, I would know what the depth is. So that's the algorithm. And in the algorithm, when we describe it to you in class or in lecture, the algorithm always works. But of course, the last point of the triangle are real images. And when you apply these algorithms to real images, you're going to find that, Professor Bobick, he just lied. Okay? In particular, what you're going to find is that to make these things work requires some reasonable amount of experimentation. So we'll give you images. In stereo, actually, we'll give you some scenes for which there exists ground truth. That is, you actually know what the right answer is, and the question will be, how close is your result to the right answer? The answer is going to be not really close. Because you're going to be implementing a relatively straightforward stereo algorithm. And the reason there are more complicated stereo algorithms out there is because the straightforward one doesn't handle all the little issues that show up in real image. This triangle of three ways of thinking about computer vision, computational models, algorithms, and real imagery, that triangle is how the course is structured. What we'll do is we'll develop the theory, which will explain to you why it's possible to compute these things, and then we'll show some algorithms that implement that theory by making certain assumptions or certain ways of going about handling the images. And then you'll actually apply them to real images, which have all of their own mysterious properties. That's going to be, we'll talk more about in a minute about the problem sets. The idea of the problem sets is to get you to understand sort of the interplay between the theory, the algorithm, and the images. The course itself is structured in these sort of 10 overall units. Don't worry, they're not all as equally long and pedantic as this introduction. We'll start off early by doing some image processing because you have to manipulate images to do a variety of types of interaction with them later. And we actually have a problem set early on there that goes from image processing to getting some basic structure. Then we'll talk about the geometry of cameras and camera models and what happens when you have multiple views and how you can relate them to each other. We'll get down in the image and talk about features, computing something about one image and figuring out where in the other image those same points occur. Because once you can do that, there's a lot you can do in terms of thinking about either transforming images or computing geometry between them. We'll spend just a little bit of time talking about how images get formed in the first place, what we call lightness and brightness. How does light interact with material and then come to your imaging sensor in order to make a picture? We'll spend a bit of time talking about motion. Remember, we talked about not just static images, but we can actually have sequences of images. So the question of how things are moving can be looked at. And these are sort of separated into motion in the image, and that is sort of how the pixels change, and then tracking the object. And we'll focus a bit on tracking as well. Then we'll get to something which we're going to do just a little bit of classification and recognition. And some of you may be saying, oh, that's disappointing. No, it's not disappointing, okay? A lot of classification and recognition is deeply steeped in machine learning. So what we'll do is we'll do some of it here, sort of some basic pattern recognition, and then computer vision applied to recognition. And then if you want to do more in the recognition universe, you'll have to learn some machine learning as well. The course concludes with just some extra stuff that is just useful to know if you're actually going to do computer vision work. And then finally, because I can't help myself, and neither can Arpan because he has true inspiration from biological systems, we'll talk a little bit about how the human vision system works. As I mentioned, the core of the doing of this class are the problem sets. It says 8. The first one is a very simple thing just to make sure that you can get your images in, do some basic manipulation of the pixels, and submit them. It's a way of making sure the mechanics of everything are working for you. Then problem sets 1 through 7 are actually to implement a variety of the algorithms that we talk about, sometimes some simplified versions of them, apply them to imagery that will give you, and see what sort of results you can get. Quick thing also, we'll be using Piazza. Piazza is a social network thing for academics. I've been using this for a couple of years now in my class here at Georgia Tech. It is a great way for students to communicate about whatever's bothering them. Now, what's bothering them? It's always the problem sets. Every now and then it's the lecture, but mostly it's the problem sets. And you'll see, Piazza